Okay, so I can read questions from here. So fine. First of all, welcome all of you to the live session of Fundamentals of Additive Manufacturing, uh, uh, 2024 code, and I have got a question here. In week 4 lecture in galvanometer topic, tan theta x value should be got in degree or in radian. Okay, please give reason for the same. So tan theta x value. So okay, this is an angle. So angle it can be, of course, in that case it was theta only if I remember correctly. But let me look into it and come back. Just let me see. And if it is mentioned, then of course you can have a look. But if it is finding inverse, it's a different thing. Let me see. Example you are saying? Okay, no issues. Yes. So yes, if it was mentioned. So the reason for it. I got your question. Let me see that example. Huh? Just give me 1 second. Let me see that example. Huh? So this was the example solved in the class, right? Let me see. Huh? Don't worry. Let me see. Four. Yeah. So this is lecture 9 or 10, I guess. One of them, I believe. Can you confirm it? Lecture 10 or 9? Yeah. It seems to be lecture 11. Last lecture. Yeah, it's 11, I guess. 11 has the galvanometer demonstration. So this must be having the same. If I am right, let me see that. Yeah. So while I explain, yes, I considered on slide number 9 that angle should be theta in degree, and that is where I am mentioning its limiting conditions. Okay. So yeah. Okay. So here it is 22.5. That in problem number which is on slide number 11 where I'm solving, it is clearly mentioned plus minus 22.5 degree. Correct. So it's given. So that it's here definitely the degree. But yes, if you are calculating it, of course, you know, for example, angle equals to arc divided by radius, right? So arc divided by radius, if you calculate from there, yes, you may need to convert it to degree. And it's just a calculation, right? I mean, it doesn't matter. Now, if I say 1045, that means you're putting 45 in degree and you are expecting the value to be 1. But if you are dealing in radian in your wherever you are calculating, you have to convert it to first radian and then get the value. So, but if you calculate it directly from that, like I said, arc divided by radius, you have to consider it in that manner. So that is always usually the radian, right? I hope I could answer that. Let me explain once again. Oh, you got it. Good to know. For example, you take an example. It's good thing that you asked out of thing. But for example, you got half a circle, right? Right. So what will be this length of half circle? You know that, correct? Now it's up to you, right? You want to mention it. Uh, I mean, it's like pi r, half of it, divide by r. What you got is pi. So now pi is, of course, 3.14. So you call it radian, but you have to then convert it to degree, right? If you really want the theta will be 180 degree. You getting it? So if half of the circle perimeter is 2 pi r, sorry, pi r, full is 2 pi r, half is pi r divided by r, what you get is pi, right? So we know that now pi in radius is 3.14 and then pi is in degree comes to be 180 degree, right? Both are correct. So you have to be careful what you are finding. I hope I could answer it. Selvarani, I hope I'm able to answer. That's a quite generic answer. It's going to be implement anywhere, if you remember. Just a simple rule. Don't get confused with that. Okay, so you said assignment now. Earlier you said lecture. So you said week 4 lecture. I was looking the example in week 4. So if you are talking about again the assignment, I need to see again what was exactly the problem you are talking about. But I'm telling you the fundamental. Try to understand it again. If I say, okay, you are traveling from this point to this point, correct? Correct. So this distance I'm giving you in mm, for example, correct? And for example, I said 3.14 mm. Right, and radius also, I said radius is also maybe whatever the radius is, doesn't matter because, and then you are dividing that r cancel, right? So that distance 3.14, what is it? It's going to be defined in radian only, nothing. So you read the question again, and I hope then you will be able to correlate. Or particularly if you can tell me exactly the question number, I'll ask and look into and provide the discussion for the whether it should be radian or the degree. But I thought you are asking for examples all in the class, and I was looking for that. But now you said assignment. So give me the number. One. Okay, in question number 1 to 7 of week 3 assignment, the range is given in degree, plus minus 22.5 degree. It's given. I just checked it. If it is another problem, give me the number. Okay. Hi, lovely. Good evening. Good evening. Good evening. So you have any doubts? You can type or you can ask whatever possible. Okay. So your doubt is, I'll look into it, huh? Yeah, if that is the case, I'll look into it, huh? I got your point. 22.5 is what? Is it degree or it's in the problem you are saying I use 22.5, whether I took it as degree or radian. I'll look into it. It looks like as in the example problem, it was not mentioned whether it is degree or radian. I can see that. So I might have considered it in radian, but I'll look into. It should be mentioned if it is given. Like it's written plus minus 22.5. Then after that, nothing is written, neither degree or radian. So maybe because 1022.5 seems to be radian if I check it on calculator. Yeah, so fine. I'll look into it and provide an explanation in the discussion forum. No issues. I got it. But usually it should be given. If it is given, you have to consider it in that. So answer is simple. It has to be given, whether it is in degree or it is in radian. We cannot assume anything. And if you have assumed that both the answers are correct, that's not an issue. So I'll look into it. So in assignment, it's written degree. In my example, I could not hear what I said, but I can see it's written just 22.5. No degree or nothing is written there. So I'll look into it. Any other doubt, please? Yes, there are few people other also joined, right? Nirmal Kumar, you have any doubt? Vinayak Patel and S. Preeti. Mhm. Yes. Is it possible to challenge the answer? Yes, yes, always you can, right? You can always. And then if we find anything wrong, we provide the bonus. Even we provide it in an announcement, as well as we accepted that there was a mistake, I think, in assignment 2. And then we realized somebody pointed it out. It was a typographical error. In the STL file, I think one of the coordinate was slightly here and there, and it was correct, but when they type it, something happened. So we accept it, and then it goes as a bonus. So shouldn't be the issue. We provide it as a bonus. We'll do that. So for assignment 3, it's not too late, right? So we can check it for assignment 3. It will be converted to a bonus for sure. But we of course will recheck it and we'll provide. Can you please provide the solution key for previous assignment? Yeah, we do. We do. Yes, so we give it to our TAs. Of course, they'll upload it. They are saying next within a week or so. We'll provide the solution. We'll provide the key. Yes. But if there is an interesting question, feel free to type it on discussion forum. We'll be happy to answer there. Yes. Yeah. Uh, yes, there is a question from Deepak. Sorry, I have to see at both places now, it seems. Sir, can a FDM machine print epoxy and copper layer? Okay, I think we haven't discussed those topics, but nowadays what can happen? First of all, of course, low melting point material is not an issue, it can print. But let me come to copper. That's more interesting question. So what you can do, directly printing copper by material extrusion is a bit challenging, though there are few processes which can extrude, but then melting it and then because metal, right? It will definitely create some issue. Otherwise, you have very high temperature ceramic nozzles. Very difficult. What could be easy way to do? What they do, they mix this powder of copper with some polymer matrix or something, maybe 80% loading or 70% loading. That 20% is just to hold those powders together. And then they convert filaments out of that. Those filaments, then they feed into FDM machines. Those are meant for handling plastics. And as the filament goes into the FDM machine, it gets melted and it melts the polymer and print it. So what you have now printed is the polymer, which is holding 80% or some percent of the copper, correct? So now after that, they put it into a furnace where this polymer is evaporated or it's gone and the sintered part later on, I mean the remaining copper or metal part gets sintered. Further, it can be melted and you can achieve a good density also. Though 100% density is quite challenging until you do an implementation like copper implementation further into the part you fabricate. So yes, possible. I will not say no, but process is not very straightforward, which you have just learned because this is quite fundamental thing we taught you. But yes, I should not say no. It is possible with that machine, but quite a long process. Yeah, could I answer it, Deepak? Yeah, thank you, Deepak. Any other questions? Please go ahead, Deepak. You are writing, Deepak, I guess. Do you have another doubt? Oh, okay. I thought you have some more questions. Okay, fine. Okay, if there are no more questions, maybe I check that in the meanwhile, Selvarani. Uh, are you saying that they have mentioned, I mean, we have mentioned in assignment 22.5 in degree, but then we solve the problem assuming 22.5 is in radian. I mean, using 0.55 we solved. We should have solved it by 0.41. That might have happened while solving. We might have by mistake calculator error, might have. So we will check that. I think you wanted to say in summary that I analyzed it. So we'll look into it. The problem should be solved by 0.4441 something, but we solved it with 0.55. Look at it. Cool. Okay. Okay. Shiva is saying, good evening, sir. Nowadays, advanced metal printing machines available in market. Through that, could we eliminate post machining technique to get required finishing? Now, देखो Shiva, what happened? What is the issue? Uh, issue is the layer thickness. Na? Uh, let us understand the fundamental. Whether in future can it do that or not? Huh? Let's talk like this. What is required? So currently you are using powder of around, let's say, 20 to 40 micron, the layer thickness, correct? Powder particle size is also near about 20 to 40 micron, right? So that layer thickness, which is of 20 to 40 micron, I cannot reduce it further. It will be very challenging. Because if you do that, in that case, you have to reduce the powder size also. Agree? And if you reduce the powder size, then spreading that powder uniformly is very difficult, because when the powder size reduces, they start getting agglomerated. Correct? And then it's very difficult to very uniformly spread it onto the XY plane. So I think this is quite a saturated and accepted in most of the 3D printer now. They are being advanced towards laser, they can produce faster. All that will happen, of course. There are a lot of scope in that direction, but reducing layer thickness further,
I see quite challenging, but I don't know right now. So layer thickness is something has to be reduced. But if you reduce layer thickness, powder particle size has to be reduced. But if you reduce powder particle size, it get agglomerated. It becomes very difficult to spread. So we are back to the same circle. So uh, not easy. We may not be able to eliminate post machining. It's one if you want to improve the surface finish. Also to eliminate support, right? Support is of course required. Some people can do, you know, nowadays low overhang printing without support, but that is also not very challenging. If you try to do that, even you get very bad surface finish onto the down skin. There are a few publications you can see, very recent ones. So again, surface finish is bad. So machining elimination is tough, but there are a few machines which I do not see much in the market or in the available, but quite interesting machines. Those are by Lumex and Sodic, though there are two companies of Japan, and they put even machining spindle inside the powder bed fusion. So spread a layer, deposit, and do machining also there itself. So it's not eliminating post processing, but it is doing it there itself. So these are the two possibilities. I hope you got it, Shiva. You get it, Shiva? Hey, yeah, I maybe would love to hear from Shiva if you can type whether you got it or not what I answered. Okay, good to know, Shiva. So anything else? Any more doubts? Please ask. Okay, I think uh, it's only you here, Shiva. Shiva, do you have any more questions you can ask? Okay, there are two questions, I guess. Sir, this course deal with the fundamental details of building AM machine. Since the price of a AM is quite high, especially I guess for metal, is it viable to build a machine by ourselves? Good question. Yeah, I don't know. Means what is expensive in that machine? Uh, I thought many times when you said metal AM, of course, we do build our own metal AM machines also based on welding. So VAM is a bit, different. Expensive when you said, mm, in what context? It's like, are we talking, I mean, the initial investment? I'll say no, not really. It's hardly 3-4 crore machine. And if you want to buy a laser, maybe of, let's say, a good laser, maybe nowadays, it maybe 10 kilowatt laser or so, it comes around the same. So that comparison of price, for example, you want to build your own? Yes, of course you can. I saw a machine in IIT Kanpur in which uh, they use the laser engraver, 100-watt laser engraver, and they use a very simple jugaad to spread the powder. And they write by the laser. And let me give you another example. Can you give me this? Yeah, look here. So some BTech students of IIT Guwahati, they printed. Let me unblur this. Yeah, you can see this. So this is plastic, correct? This is called TPU. And you know how these shapes were built? They were built by students, in their balcony in hostels. And what they use to melt this powder? Sunlight. Sunlight goes through a lens, and that lens just focus that sunlight and melt it. And I have seen a video, and I think you can also search on YouTube. Somebody has melted even the sand by using that sunlight. So it depends. I mean, if you call laser expensive because we export laser a lot. If you really want to target now to reduce the price, I think we can manage the software. We are good in it because we are not bothered because we don't have indigenous machines so far. Even if you build indigenous machines, where is the laser? We have to target making laser. But then again, we need, recently I learned to create that wealth around so that you can afford building your own laser. So you will find in the end, even you decided today, you have to import laser. If it is like good high powered laser. I'm not aware many of the Indian manufacturers of laser, or they are not actually. So it's good. It's a good time. We think about building our own laser, then only the price will come down. Otherwise, what is there in that machine? Nothing. It's just single axis machine, moving platform up and down. Of course, back and forth doesn't stop in between. It's just from one end to another and PLC based thing. It's not a programmable thing. And it's not expensive. It depends what sophistication level you want. You don't want to put more head into it. So yeah. So yes, why not build it? The answer is build it. And you can choose multiple options. Then only you become innovative. Na? But optics is the second thing. We again import the optics, the galvanometer. For that, we need to have a very good finish on that optics, handling high power, then F theta lens. You see the complexity, na? The goal of this course was to tell you that so many things are there. It's not like press the button, it works. It of course works, but then there is a lot of things inside. F theta lens, you know now why the size is limited to 250 by 250. It could be bigger than that, right? But then how will I have that F theta lens of that large? So they put multiples. Even if why the laser power is limited to 600 watt, it could be more, but then a lot of cooling is required for the optics. So yeah, maybe you can start with DED. It's easier to build, and then you can go with powder bed. Like I said, this way, use a 100-watt laser, make an indigenous mechanism to spread the powder. Maybe manually, do it manually. Maybe deposit 5-6 layers. Okay, but then you can build things like this. So this, I'm very proud to these students, the BTech students who built this 3D printer in their balcony and printed parts using sunlight at IIT Guwahati. So very happy with them, with by their work. So you build, yes, of course. Then you learn. Deepak, and few more questions now. I think I missed it here. I back to this. I clearly understood with powder bed fusion technique, sir. Could you explain this issue with wire arc additive manufacturing? Oh, which issue, right? Which issue? Expensive ones. Shiva, just quickly write which issue. I forgot. Are you referring to the discussion I was answering for Silverani? I'll come back to your question. Huh? Sir, to get electrically continuity by the method you said previously, what kind of post processing will be required? Again, what I said. Sir, to get electrically continuity. Deepak, for copper layer, acha. Why do you need electric continuity here? Laser does not require, right? Laser can fall. It doesn't require a loop to control. So why do you need the conductivity? Why you are bothered about the conductivity? Electrical continuity, I mean, or whatever. Can you elaborate more, Deepak? I didn't get your question also. Good evening, sir. Can we say metal powder bed fusion are starting to get commercialized? Yes, of course. They are huge, available. I mean, I believe not only here in US as well. They are widely accepted because again, remember one thing. I think this I have not explained, and I learned it in last few years. Machines, those are just required the press the button, sit back. You can't do anything in between. The intervention is not there. It's not allowing, or it's not possible because of the architecture of the machine. Such machines are more popular because it requires less skilled people. Of course, you need to have skill in CAD, but then again, you can't do much with that. So yes, it was fully automatic machine. Press button, sit back, relax, it will print. Come back in the morning, nothing will happen. No collision. If there will be minor collision, it will stop. But it is not the case with robotic DED. Robot with laser head depositing. It required extensive skills on programming side, as well as when you deposit, it may do something wrong as well. It can hit. It's just like you have JCB, but you don't have drivers, right? So you have to get trained on robots, on WAM, and then it really works. So that's why, in academia, WAM is more popular nowadays because it challenge the researchers, and we like to be challenged, right? Because in powder bed machine, what can I do? Maybe I can change powder and I can do some metallurgical analysis. Of course, in that direction, it's extremely good. You can develop new alloys, high entropy alloys and all. But for WAM, even running the machine is a challenge. So there are a lot beyond other than metallurgical aspects in WAM. Build strategies, open up new areas. You can create FGMs, you can repair parts, you can do cladding with the same machine. So can we say metal powder processes are getting, yes, they are getting commercialized a lot. As a follow-up question, which metal alloy powder are extremely difficult to manufacture? Oh, again, copper, because copper is highly reflective. And many people nowadays on LinkedIn post, now we are able to print copper. So that means it is a benchmark. So that's very challenging material because it does not absorb much of the material. It reflects a lot laser, but then of course nowadays they have blue laser and they have good strategies to do that. Other than that, I'll say any high melting point material, right? Maybe material which has very high tendency for precipitating, and material those are very sensitive for rapid cooling. They produce crack. So I'll say challenges everywhere. If it is a new material, it is going to be challenging. There is nothing easy. Easy means you know the parameter, na? or somebody has spent time to bring those parameters. So any new material will be challenging. Or these high entropy alloys are even more challenging. Or sometimes they blend 2, 3 materials and then do. That's another challenge because it may give you good results and different results. But then again, of course, you have to find. So challenge is only if the material is not explored. Otherwise, yeah. So I hope I answered it to AC. And Shiva, post machining technique in VAM. Oh, you might be referring. Yeah, you clearly understood that powder bed fusion technologies with that issue. But VAM में कैसे कर सकते हैं, right? You're asking how can I eliminate? No, VAM is even worse to produce the high finish because the layer thickness is around 1 mm with 1.2 mm diameter wire. Now you can say, sir, why don't I use lesser diameter wire? Now I'll tell you a lot of issues. If it is a MIG welding process, the arc will not stable. If it is less than maybe 0.8, it will create an issue. But let us assume that you said, okay, sir, let us not use MIG welding. We can use TIG welding or plasma. And then I can feed wire into it and I'll deposit. Fine, you can. I have seen it. I have seen it in Fraunhofer where they use the wire, which is around 0.2 mm, I guess, and then feed in laser. So quite possible. You can feed it in plasma also. And maybe microplasma you can talk about. Yes, you can. Then again, it is thin wire, 0.2. Imagine that wire will be having some curvature. It has to hit very tiny melt pool. Maybe you say 1 mm melt pool, let's say, or maybe 0.5 mm melt pool. And it's going to hit that. And accurately it has to hit means it has to come in a straight manner. So first you require a lot of straighteners. Feeding become quite challenging. If it goes here and there, gone. So that's why even I do not even look these processes to be, VAM-like processes to be used for low layer thickness or low deposition rate. They are meant to deposit high deposition rate, very high deposition rate, quickly build part, take these machines out, get the things repair on site, build the bridges, right? All that high-end application is VAM for. So that, am I disconnected or what? No, acha, fine. Okay, I'm back. Yeah. So I hope I could answer. So post machining is required, but then one more interesting thing, let me tell you, Shiva. For example, you take an example of a robotic arm. Okay, bhai. That robotic arm required machining where? Only where the bearing is going to fit or the motor is going to be attached. Rest of the portion, why do you even need machining? Or let me talk about a bridge made by VAM. Why do you need machining on that? Let it be rough. What is the issue? So localize for the whole thing. I'll do machining wherever it's required. And for that, I don't think I should bother about. I want high productivity. It's getting frozen in between. Anyway, I hope I could answer your question, Shiva and AC. I don't know your full name. Thank you, Selvarani said. Great work. Thank you. I'll convey this to my students. They already left, but I'll inform them. Yeah, VAM is popular. Yeah, VAM is quite popular nowadays. Yes, everybody is talking about VAM. A lot about VAM. I'm very happy to know that. Hey, I think it was a very interesting session. We had a good discussion on time. Identify is more important. Okay. So thank you. You can keep posting on, on discussion forum as well. Any doubt, happy to answer such. These are interesting questions. Good, happy to answer such question. Yeah, thank you, Shiva. Thank you. We can stop here if you want. Sorry. Because this is not continuous. I'm seeing a lot of video pause on YouTube as well. I don't know, some issues seems to be with internet, I believe. It's pausing a lot, it's buffering a lot. Yeah, thank you, Deepak. Thank you. Thank you, Shiva. Thank you. Thank you. Thank you, Shiva. So we can stop here, I guess, now. We had a good discussion. Yeah. Okay, sir. Thank you. See you in the next live session.